Welcome to this explainer. Today, we're unlocking what I genuinely like to call a mathematical superpower. We're going to build a tool that takes completely impossible calculus problems and makes them, well, entirely solvable. So let's just dive right into this. Imagine you're an engineer or maybe a scientist and you're staring down this exact problem. How do you integrate a function that has 0 elementary antiderivatives, something like 1 over the quantity 1 plus x to the 7th? I mean, you can't use u substitution, integration by parts, nope, that's a dead end too. But what if I told you there's actually a hidden backdoor to solve this?
Here's our roadmap for today. First, we'll meet the power series. Then, we'll cover the limits of convergence, check out some functions in disguise, do a little calculus on power series, and finally, unleash the ultimate math superpower.
All right, part 1. Meet the power series.
So what is it? A power series is essentially an infinite polynomial. If you check out the equation we have set up here, you'll see we have constants acting as our coefficients, that's the Cn, a center point a, and our variable x. Now, instead of stopping at x squared or x cubed, like your standard run-of-the-mill polynomial, this series literally just keeps going forever. It's a really elegant way to represent complex, curvy functions using simple, repeating algebraic terms.
And this right here brilliantly illustrates the magic of what a power series actually does. We can take a standard rational function, like 1 over 1 minus x, and equate it to the infinite geometric series, 1 plus x squared, and so on. As long as the absolute value of x is less than 1, these two sides are mathematically identical. Honestly, they're two sides of the exact same coin. A complex rational function is secretly just an infinite polynomial waiting to be unwrapped.
Moving on to part 2. The limits of convergence. Now, every superpower has its limits, right? So the absolutely crucial thing to know here is the radius of convergence, which we denote as r. You can think of this as the safe zone. If your x value falls within this distance from the center A, the infinite series behaves itself. It converges nicely to a real finite number. But the very second you step outside this strict boundary, the whole infinite sum spirals completely out of control to infinity. It diverges and, well, the math basically becomes useless.
So, how exactly do we find this safe zone? Well, we have a highly reliable 3-step algorithm. Step 1. Apply the ratio test. We take the limit as n approaches infinity of the absolute value of the next term divided by the current term. Step 2. Set that resulting limit to be strictly less than 1. Solving that inequality is what gives us our open interval. But step 3, this is where people always trip up. You have to manually test the exact boundary points, the endpoints, separately, because the ratio test is entirely inconclusive right there.
Let's build up some intuition with a concrete example. Take a look at the equation for the series of x minus 3 to the power of n, all divided by n. If we run our handy ratio test on this, the math neatly simplifies down to the absolute value of x minus 3 is less than 1. And solving that basic inequality tells us our safe zone, our open interval, is between x equals 2 and x equals 4. But remember, we are not done yet.
We have to check those boundaries. If we plug x equals 4 back into our original series, we get the harmonic series, the sum of 1 over n, which is famously absolutely divergent. So 4 is out. No way. But if we plug in x equals 2, we get an alternating series, which actually converges, so 2 is safely included. That means our final interval of convergence includes 2, but strictly excludes 4. The lesson here? Always, always check your endpoints.
Notice how different series have wildly different behaviors? The geometric series, in our first example, has a neat little radius of 1. But look at the second one. Putting an n factorial in the numerator means this series explodes instantly. It only converges at the exact center, 0. Conversely, if that factorial is in the denominator, like in our third example, the radius becomes infinite. It safely converges for absolutely every real number you could possibly think to plug into it. Pretty wild, right?
Okay, part 3. Functions in disguise.
Suppose our goal here is to express the rational function 1 over 1 plus x squared as an infinite series. The clever trick is to realize this looks awfully similar to our geometric series prototype, 1 over 1 minus r. So all we have to do is take our geometric formula and substitute r with negative x squared. It is a remarkably simple algebraic swap.
And by making that substitution, as you can see in the result, we prove that this rational function is secretly just an alternating power series in disguise. We get 1 minus x squared plus x to the 4th minus x to the 6th, and so on. We've successfully disguised the function while keeping an interval of -1 to 1. This kind of shape-shifting technique is incredibly powerful in complex analysis.
Moving right along to Section 4, Calculus on Power Series.
Now here is the real beauty of it all. To take the derivative of a power series, you literally just differentiate it term by term. The exponent n simply drops down to the front, and the new power becomes n minus 1. It is exactly the same standard power rule you learned for basic finite polynomials in early calculus. We're just applying it infinitely.
And integration works exactly the same way. Just add 1 to the exponent, divide by the new exponent, and, obviously don't forget your constant of integration c. But the most remarkable part here is that when you differentiate or integrate, the radius of convergence, that crucial r value we calculated earlier, remains completely unchanged. The size of your safe zone stays exactly the same.
However, I definitely have to warn you about a sneaky little trap here. While the overall radius stays the same, the behavior at the exact boundaries can actually shift. Differentiation is a bit destructive. It can make you lose convergence at an endpoint. Integration, on the other hand, is much more forgiving. It can actually help you gain convergence at an endpoint. So the big takeaway? If you perform calculus on a series, you absolutely have to retest those boundary endpoints.
Finally, Part 5. The ultimate math superpower.
So here it is again, that seemingly impossible integral from the beginning, 1 over 1 plus x to the 7th. Instead of panicking, we are going to use our new shape-shifting skills. Step 1. We recognize the geometric pattern and substitute negative x to the 7th into our series formula. Instantly, our terrifying rational function breaks down into a totally manageable, alternating infinite polynomial. Look at that equation. So much better, right?
Step 2. We use our new calculus rules and integrate term by term. Instead of pulling our hair out over advanced integration techniques, we literally just use the basic power rule right on the series. We add 1 to the exponent, 7n, making it 7n plus 1, and then divide by that exact new exponent. And just like that, we have a perfectly valid antiderivative equation, provided the absolute value of x is less than 1.
Now, what if we needed to evaluate this as a definite integral, say from 0 to 0.5? Well, by summing just the very first 3 terms of our new series, literally just plugging in n equals 0, 1, and 2, we arrive at this wonderfully precise approximation, 0.4995. We took a problem that literally could not be solved with traditional calculus, and we turned it into basic arithmetic.
But you might be wondering, how do we know this number is actually reliable? Well, because of the alternating series estimation theorem. It mathematically guarantees that our error is always less than or equal to the very first term we left out. If we check the next term in our sequence, where n equals 3, the value is roughly 1.08 times 10 to the negative 8th. This proves that our simple 3-term answer is flawlessly accurate to within 1/10,000,000th. That is insane precision.
And honestly, this brilliantly illustrates the big picture. When your computer or your calculator spits out the value for sine, cosine, or some impossible integral, it is not looking up a massive static table of numbers. It is using power series. These aren't just intimidating infinite sums you see in a textbook, they are the hidden machinery, the literal superpowers, quietly calculating the digital world all around you. So the next time you hit equals on a calculator, ask yourself, what infinite series just ran in the background to give you that exact answer? Keep exploring, and I'll see you in the next explainer.